Hello, welcome to a new lesson in thermodynamics. Today we are going to talk about the van der Waals gas, and we are going to use some results of a previous lesson that we made where we derived some important relations on the thermodynamical properties of the real gas. In particular, we found out that the heat capacity of the ideal gas is constant if there are changes in the volume of the gas, right? And then we gave some expressions to calculate the internal energy of the system, which is again a real gas. So we want to apply this knowledge to now the van der Waals gas. Okay, so the first thing we need to say is that the van der Waals gas equation reads P plus N divided by V squared times A times B minus NB equals to NKT. Okay, here, of course, P is the pressure, V is the volume, N is the number of moles, and T is the temperature. And you can see that there are two parameters, A and B, that are kind of parameters to make some corrections on the pressure and the volume. I mean that, for example, in the van der Waals gas, we take into consideration that between molecules there are interactions, right? So that there is an additional pressure that we need to take into account, right? And that correction due to those interactions is quantified by this thing over here, which is n squared divided by v squared times a. And something that we can notice is that, for example, if a is equal to 0 and b is equal to 0, then we get the product P times B, which is an element of the equation of state of an ideal gas, right? Okay, and B is a parameter that has to do something with a correction, but now in the volume of the gas, again, due to the microscopic volume of the molecules that compose the gas. Okay, so you just need to remember that A and B are parameters to make some corrections to get a more accurate expression for the pressure and the volume, and then we construct the new equation of a state, but now it's a little different, right? So this is the van der Waals equation. Just like a quick explanation about what is it about. So on that first lesson, we were talking about the internal energy, and we said that the differential of internal energy du can be written as the derivative of u with respect to b dv plus the derivative of u with respect to t dt, and we define the heat capacity of the gas as Cv equals to the derivative of u with respect to t, right? And that means that we can rewrite this as the derivative of u with respect to b dv plus Cv times dt. And then, using some laws of thermodynamics and the entropy of the system, we found out that we can express this partial derivative, the derivative of u with respect to b, as T times the derivative of the pressure with respect to the temperature minus the pressure. And the thing here is that this expression allows us to specify the derivative of u with respect to b in terms of state variables, right? Because looking that p is not a state variable, we should be able to express p in terms of b and t, right? So that this expression at the end is an expression that only depends on b and t. Okay. And that expression, actually, P of B and T, is known as the equation of state of the gas, right? With the ideal gas, we used PV equals NKT, but now here we are working with the van der Waals gas, so that we need to solve this equation for P just to be able to express P in terms of B and T, right? So I think it's not too hard to see that P is equal to NKT divided by V minus NB minus N divided by V squared times A. So with this, we can calculate the partial derivative of P with respect to T, and that is going to be NK divided by V minus NB. Okay, and then with this information, now we can calculate the derivative of the internal energy with respect to the volume, so that this is T times Nk divided by V minus Nv minus P, right? But P is, well, this definition. So it is Nkt divided by V minus Nv minus N divided by V squared A. Perfect. So from here, it's easy to see that we can cancel these two elements. And then the derivative of U with respect to B is equal to N divided by V squared times A. Okay, perfect. So what happens if we take this back into the du definition? Well, we are going to get that du is equal to cb dt plus n divided by v squared a db, right? Okay, so this is like the exact differential, or the differential of internal energy for the van der Waals gas. Okay, remember that when you have the total differential of a function given as a function of x comma y times dx, and then another function of x comma y times dy, looking that this is an exact differential, it follows that the derivative of m with respect to y is equal to the derivative of n with respect to x, right? So if we apply this knowledge to our du, we get easily that the derivative of cb with respect to b, recall that this is the derivative, you need to take the derivative with respect to the variable of the other differential element, right? In this case, for this one will be the volume, and for this one it will be the temperature. So this will be the derivative of the heat capacity with respect to B is equal to the derivative with respect to T of N divided by B squared times A, right? And looking that this doesn't depend on the temperature, obviously this thing is equal to 0. And remember that on the previous lesson, we got to the result that the heat capacity doesn't change with volume, right? So for the ideal gas, if you expand it or compress it, its heat capacity is going to remain constant. That is not going to change, right? So it turns out that for the van der Waals gas, it happens the same. And we have a constant heat capacity in volume. So I think it's a very interesting result. Okay, so another thing that I wanted to show in this lesson is that if we begin from the expression for the du element, again, looking that we know that the internal energy is integrable, I mean, it's an exact differential, we can integrate each part of this equation, right? I mean that we can take the integral on each element of this sum, like this, and we are going to get a valid result. That is what it means to be integrable. And just by taking into consideration the correct limits of integration, right? So just to establish what are those limits, we need to think what we are studying. I mean, we are working on a gas that is a thermodynamical system that is specified by variables of state variables. So this means that we have a process that begins with some specific configuration that we can define as U0, T0, and B0, right? This is like the initial state of the system, and then it evolves in time so that we get to the configuration where the system has an energy U, a temperature T, and a volume V, right? These three variables all match at the same time. And these other three also match at the same time. Actually, remember that the internal energy is a function of T and B. So in practice, we actually only need to specify two variables, T0 and B0, that evolves to T and B. Okay, perfect. So this is telling us already what limits of integration we need to use, right? Because if we are taking an integral of the change in the internal energy, then this change goes from an initial internal energy U0 to some internal energy U. And then from this one, looking that the integral is on the temperature, well, we start from an initial temperature T0, and then we end at some specific temperature T. And for the other integral, we have something similar, but from an initial volume to a final volume b. Perfect. So this is telling us that to find the internal energy at any moment of the process, we just need to calculate those integrals over there. So what are we going to get? Well, we get that for the first integral, we have u minus u0. Remember that this is a function of the state variables. So this is u of t comma b minus u0 of t0 comma b0, right? Perfect. So this is going to be equal to, well, the integral of the heat capacity in the temperature domain, right? So in principle, and we do not know what is the expression for the heat capacity in terms of the temperature, we should think that it must depend on the temperature. We haven't said anything about this, but we can think that maybe, yeah, the heat capacity depends on the temperature, right? So in principle, we do not know how to calculate this integral. But what we do know is that from the experiments, we say that for a little change in temperature, the heat capacity behaves almost like a constant variable, right? Remember, this is just for little changes in temperature. So if we consider that, we can just take the heat capacity out of the integral to get that this is Cv, and then the integral from t0 to t of dt, which we know that is only t minus t0, right? And then we just need to take this other integral, which is a very easy integral. In this case, recall, well, we do have an expression for the volume inside the integral, so I think it's not very hard to see that this is going to be n squared a and then minus 1 divided by v from b0 to b, right? That is the integral of n squared divided by b squared a with respect to the volume. Okay, so from here we can rewrite this expression as the change in the internal energy times the heat capacity times some change in the temperature, right? Like this, and then plus n squared a, and then we will get minus 1 divided by v minus times the minus of the fundamental theorem of calculus. We have plus 1 divided by v0. And if we factor a minus sign in the last expression, we will get that the change in internal energy is equal to the heat capacity times the change in the temperature minus n squared a times 1 divided by v minus 1 divided by v0, which is the initial volume. Right, so this expression is telling us how the internal energy changes between the process that goes from t0, b0 to t comma b, right? If we want to know the specific internal energy, then we use this shape of the equation where we do not consider the change, but the function of the internal energy itself. Okay, perfect. So what happens if we consider big volumes, for example, just by looking to this expression? We can say that if the volume is very big, these two elements tend to 0, right? So this whole piece is going to be equal to 0, so that we get that the change in the internal energy is equal to the heat capacity times the change in the temperature. And I think that in the previous lesson, we didn't mention this characteristic for the ideal gas, but it turns out that the behavior of the van der Waals gas is equal to the behavior of the ideal gas, where the heat capacity can be seen as some change in the internal energy divided by the change in the temperature, right? So the thing here is that for big volumes, the van der Waals gas has a behavior that is equal to the behavior of the ideal gas, right? Other thing is that if we do not consider a big volume for the initial volume, but B increases, right? Then if B is big, this element is going to be equal to 0, right? As I mean that the bigger B becomes, this whole element is going to be smaller and smaller, right? So that we are subtracting a quantity that is being smaller. The thing here is that That means that the internal energy increases if we increase the volume, right? Okay, I think that those increments are not too big, but it is telling us that the internal energy actually is increasing with the volume. Okay, perfect. So I think this is the final important result of the lesson. Remember that it's the change in the internal energy of a van der Waals gas given in terms of the state variables, the temperature and the volume. Okay, thank you so much for watching.